The universe is expanding, but expanding into what beyond every galaxy space itself stretches farther and faster than light can reach. Tonight we'll explore one of the strangest questions in all of science. If you enjoy mysteries like this, please like, subscribe and share, and tell us in the comments, what do you think lies beyond the edge of the universe? Thank you for watching. Now, let's begin. The night sky appears steady to the eye, yet careful measurement shows that the scale of the cosmos changes with time. Astronomers compare the light from distant galaxies to the light from familiar elements studied in laboratories on Earth, and find that the signature lines arrive shifted toward longer wavelengths. This shift, called redshift, grows with distance in a smooth and repeatable way across the sky. The pattern does not point away from a single central place, and it does not resemble the flow of projectiles through a fixed stage. Instead, it looks like a quiet broadening of the stage itself, a change in the way large distances are measured. When a spectrum is recorded from a far galaxy, the positions of its lines tell how much the wave crests have been stretched during their journey. The longer the travel time, the more stretching is seen, and the more the universe has grown while the light has been in flight. In this sense, a spectrum becomes both a ruler and a clock. It carries the imprint of the atoms where the light was made, and it also carries a record of the gradual widening of the cosmic scale between emission and observation. The sky is surveyed in many directions to test whether this behavior might be a local effect, perhaps caused by our own motion, or by a patch of matter that tugs on nearby galaxies. The surveys show that after small corrections for local motions, the same relation between distance and redshift holds again and again. This relation is known as the Hubble-Lemaitre law. It states in plain terms that the farther a galaxy lies, the faster it appears to recede when the shift in its light is interpreted through the expansion picture. The word recede can be misleading if taken as ordinary motion. A galaxy that follows the general cosmic flow need not plough through surrounding space like a craft through water. The large-scale picture is quieter. The distances between widely separated points grow because the standard for measuring those distances grows. Astronomers describe this growth with a function of time called the scale factor. Although the formal mathematics belongs to later sections, the physical meaning is simple. Imagine two far-separated galaxies that feel no strong local pull toward one another and no strong push apart from nearby structures. At an earlier moment they are separated by some distance. At a later moment they are separated by a larger distance. The ratio of those two distances equals the ratio of the scale factor at the two moments. If the scale factor doubles, the separation doubles, not because either galaxy has sprinted through space, but because the metric that defines distance on the largest scales now assigns a larger value to the interval between them. This is why the observed redshift relates so naturally to distance. A photon's wavelength is part of the metric story. As the scale grows, the spacing between wave crests grows with it. By reading that growth in the spectrum, observers can infer how the scale has changed while the photon has crossed intergalactic space. The idea that the metric changes rather than galaxies streaming through an unchanging arena also explains why the expansion does not select a special center. When the view is restricted to regions small compared with the observable horizon, each location sees distant galaxies drift away in a pattern that looks the same in every direction. No vantage point is singled out by the data. The Milky Way is not at the hub. Neither is any other ordinary galaxy. Uniformity on the larger scales tested by mapping many parts of the sky supports the conclusion that the expansion is a property of the cosmic geometry itself. A common analogy can help if it is kept precise and limited. On the surface of a balloon covered with tiny dots, the distance between any two widely separated dots increases as the balloon inflates. No dot sits at the center on the surface. Each dot sees the others recede, and the greater the separation, the greater the rate of increase. The surface does not need an edge on the surface, and it does not need to move into a surface of higher dimension to define its own distances. The analogy is only a guide, not a literal description of our three-dimensional space. Yet it captures the essential point that expansion is a change in measured separations, rather than a wind-pushing objects through a fixed background. Observers work to ensure that what they call redshift is not confused by dust that dims and reddens light, or by gas that can add or subtract features from a spectrum. They use multiple parts of the spectrum, they repeat measurements with different telescopes, and they compare results from independent surveys. They also build distance estimates in several independent ways so that no single method controls the result. When these checks are made, the same broad picture stands. The universe shows a near-linear relation between distance and redshift, for systems not too far away, and a consistent extension of that relation at greater ranges once curvature composition and the full expansion history are taken into account. In daily language, one might be tempted to ask what the universe expands into. The observations that define expansion do not require an outside chamber. They require only that the rules by which distance is measured on the larger scales change smoothly with time. Within a galaxy, stars orbit under gravity and do not drift apart with the expansion, because local binding dominates. Within small groups of galaxies, similar binding can hold neighbors together. These local exceptions do not contradict the global trend. On scales far greater than those of clusters, the average separation between co-moving points increases as the scale factor grows, and that increase is what the sky records in the stretch of light. The picture that emerges in this opening view is therefore strictly observational. The cosmos that instruments reveal is not static. It is not exploding from a location into a surrounding emptiness. It is a self-consistent geometry in which large-scale distances grow with time, and that growth leaves a clear signal in the light that has crossed the deep sky to reach present instruments. With this description in place, further sections can turn to the language used to model the geometry, and to the careful distinction between motion through space and the evolution of space itself, while this first step remains anchored to what the measurements quietly show. Astronomers learn the scale of the universe by building a careful sequence of methods that reach from nearby space to the farthest measurable distances, each step anchored to the ones before it, so that uncertainties do not multiply without control. The lowest rungs concern distances that can be measured by geometry alone. Within the solar system, radar pulses sent to nearby planets travel out and back, and their round-trip times set distances in terms of the speed of light. This establishes a meter stick for the planetary neighborhood and fixes the size of Earth's orbit. With that orbit known, a wider geometric method becomes possible. As Earth moves from one side of the Sun to the other, a nearby star appears to shift against the deeper pattern of more distant stars. This tiny apparent shift is called parallax. The angle is small, but modern instruments measure it with high precision. Because the baseline is the diameter of Earth's orbit, the measured angle gives a distance by plane trigonometry. In this way, geometric distances reach out to a large set of nearby stars. These distances do not depend on the brightness of those stars or on any assumption about how stars behave. They depend only on measured angles and the known size of Earth's path around the Sun. Once a network of nearby stars has secured distances, their light can be used to teach the next method how to behave. Some stars vary in brightness in a regular way. For a special class of pulsating stars, the period of pulsation relates to the true power of the star. If the true power is known, then the observed brightness sets a distance. These variable stars therefore become standard candles in a calibrated sense. They are not assumed to be identical. Rather, their periods point to their true powers. The absolute scale of those powers is set by the geometric parallax distances of nearby examples. By collecting many such stars in our galaxy and in neighbouring galaxies, observers extend reliable distances to systems far beyond the reach of direct parallax. Star clusters provide another rung. The colour and brightness distribution of stars within a cluster follows patterns understood from stellar evolution. When the distance to a few clusters is known from parallax or from variable stars within them, the same patterns can be used to estimate distances to similar clusters elsewhere. In galaxies that are close enough for individual bright stars to be resolved, the tips of the red giant branches in their stellar populations provide a nearly standard candle, because the physics of how these stars ignite helium places a characteristic ceiling on their brightness. The brightness of that feature once calibrated nearby yields distances to more remote galaxies, where single stars are still observable as points. When individual stars blur together and galaxies become smooth patches of light, another method steps in. Small fluctuations in surface brightness across a galaxy arise from the statistics of how many stars fall within each resolution element. The size of those fluctuations scales with distance because farther galaxies are blurred, more and many more stars fall within each patch on the detector. After calibration in nearby systems, this surface brightness fluctuation method reaches farther still. The ladder continues with relations that tie a galaxy's internal dynamics to its luminosity. Spiral galaxies show a well-tested link between their rotation speeds and their total light output. If the rotation speed is measured from spectral line widths, and if the relation is calibrated using galaxies of known distance, then the observed brightness of a similar spiral galaxy yields a distance. Elliptical galaxies show a different relation that links their characteristic stellar speeds and sizes to their light output, and that relation can be used in the same stepwise way once its scale has been established. With these tools, distances spread outward across the local universe and reach many tens and then hundreds of millions of light years. Beyond those ranges, the sky offers brief but powerful beacons. Some white dwarf stars in close binary systems accumulate matter from their companions until a runaway thermonuclear event ignites. The resulting supernova presents a characteristic light curve and color evolution that allow its true power to be standardized through observed features. When these events occur in galaxies whose distances have been fixed by the lower rungs of the ladder, they provide a firm calibration for how bright they truly are. Then, when a similar event is observed at great distance, its measured brightness and color, after corrections for intervening dust, set a distance that can reach across billions of light years. These supernovae serve as probes of the expansion history itself because their distances can be compared to the redshifts of their host galaxies. Alongside these methods, astronomers cultivate geometric anchors that do not rely on brightness at all. Very long baseline. Interferometry measures the apparent motions of matter spots within rotating disks of gas near the centers of some galaxies. The angular motions across the sky and the line of sight velocities together provide a direct geometric distance to those galaxies. When such a distance is available, it ties the ladder to firm geometry far beyond the reach of stellar parallax. The purpose of building many rungs is not only to reach farther, but also to cross-check at every step. If different methods agree where they overlap, confidence grows that hidden biases are under control. Dust can dim light and make a galaxy appear farther than it is, So observers measure in several parts of the spectrum and apply models of how dust affects colours to remove its influence. Selection effects can make samples unrepresentative, so surveys are designed to include both bright and faint targets across wide areas. The local motions of galaxies within groups can add or subtract from the general expansion signal, so distances are averaged over large volumes to reduce this noise. Each method carries its own systematic uncertainties, but their combination becomes stronger than any single approach would be. As distances extend and as redshifts are measured for the same systems, a nearly linear relation appears at modest distances, which is the low distance limit of the general law that links the change of the scale factor to the separation of co-moving points. At greater distances, the light path samples earlier epochs when the scale factor was smaller, and the relation bends in ways that record the integrated expansion history and the influence of matter and radiation and the energy that drives late-time acceleration. The ladder does not end at a final rung. Instead, it merges into the broader framework of cosmological mapping. Galaxy redshift surveys trace a web of structure whose scale can be compared to standard rulers that were set in the early universe. The cosmic microwave background provides an anchor at a time when light last scattered from matter in a nearly uniform plasma. Distances derived from the ladder to that time and beyond are not literal travel times for any craft, but measured consequences of the changing metric. The power of the ladder lies in its humility. Each rung is simple enough to be tested, each is tied to prior steps, and each is used only within the range where it has been proven reliable. In this way, the story of expansion moves from a hint in a spectrum to a measured history of how the scale of the universe changes with time, all without invoking an outside space into which the universe must grow. The ladder builds a self-consistent map whose distances are defined within the very geometry that evolves, and whose reliability rests on many independent threads woven together with patience and care. The relation between distance and redshift that careful surveys reveal takes a simple form at modest ranges. In that regime, a galaxy's apparent recession speed grows in direct proportion to its distance, and the constant that links the two is called the Hubble parameter as measured in the present era. In plain terms, when the distance doubles, the recession speed about doubles. This statement does not describe engines or rockets. It describes how the cosmic measuring tape itself stretches with time so that widely separated points drift apart even when they are not moving through space in the ordinary sense. Light from a distant galaxy carries the record of that stretching. The positions of spectral lines shift to longer wavelengths in proportion to how much the scale has grown while the light was crossing intergalactic space. Nearby systems show small shifts. More distant systems show larger shifts. When these shifts are translated into an apparent speed and compared with independently measured distances, the points fall close to a straight line that passes through the origin. The slope of this line is the present Hubble parameter. At very small distances, motions caused by local gravity can blur the pattern. Galaxies tug one another inside groups and clusters so that their spectra record both the general expansion and these smaller scale motions. To reduce this blur, observers select systems far enough away that local motions are a small fraction of the overall signal, and they average over many directions to allow random motions to cancel. In addition, they define a sensible frame of rest. Earth circles the Sun. The Sun orbits within the Milky Way. The Milky Way drifts within its local group. All of these motions leave small measurable imprints in spectra and in the pattern of the ancient radiation that fills space. By correcting for these effects, observers place their measurements in a frame tied to the large-scale flow of the cosmos, rather than to the motion of a single planet or a single galaxy. The law's meaning depends on clear definitions of distance and speed in a universe whose geometry evolves. Distance in this context refers to the separation between two comoving points at one agreed upon cosmic time, not the path that light travels, which is longer, because the scale grows while the photon is in flight. Speed refers to the rate at which that separation increases because the scale itself changes not to a wind that pushes galaxies through space. When this is kept in mind, the straight line acquires a precise interpretation. It does not point to a central location. It does not imply an edge. It records a uniform fractional growth of large-scale separations that any typical observer would measure. An astronomer in a distant ordinary galaxy, after making the same local corrections, would plot the same line with the same slope within the same nearby range. The slope is called the present Hubble parameter because it describes the rate of change of the scale today. It is not fixed for all cosmic time. When the universe is younger and matter and radiation are more dense, gravity slows the growth more strongly, and the rate is larger in simple units of distance per time per distance. At later times, the influence called dark energy modifies the rate, and in the present era leads to gentle speeding up. As observers look farther away, they look back to epochs when the rate is different, so the simple linear relation bends in ways that record the full expansion history. At modest distances, however, the linear law is an excellent description and serves as the gateway from raw spectra to a quantitative measure of how the cosmic scale changes with time. Measuring the slope requires two ingredients, distances and redshifts for the same objects. Distances come from the ladder described in the prior section, which begins with geometry near the Sun, extends through parallax to nearby stars, and then uses calibrated standard candles and other methods to reach other galaxies. Redshifts come from spectra that reveal how familiar atomic lines have been stretched. For each galaxy, a distance is paired with a redshift and converted into an apparent recession speed appropriate to the nearby law. When these pairs are plotted, the trend emerges. The more pairs that can be measured with care, the more strongly the straight line reveals itself. Surveys design their samples to include galaxies across a wide spread of distances to avoid biases toward only bright or easy targets, and to cover the sky broadly so that no single region dominates the fit. Even with care, sources of bias must be addressed. Dust in and between galaxies dims light and changes colors, which can make objects appear farther than they are if not corrected. Gas along the line of sight can add or alter spectral features and affect redshift estimates. Selection rules can quietly favor galaxies that are easier to measure, potentially skewing the result. To control these effects, observers measure in several bands of light, apply physically motivated models of how dust changes colors, test those models in nearby systems where distances are secure, and repeat observations with different instruments and methods. Independent teams build their own catalogues and compare results. Agreement across such efforts strengthens confidence that no hidden bias dominates the slope. The meaning of the slope is best stated without metaphor, yet a restrained picture can help. Imagine a flexible grid that stretches uniformly in all directions. The dots that mark galaxies do not crawl across the grid, but the spacing between any pair of dots grows as the grid stretches. If the grid stretches by a fixed fraction per unit time, then the rate at which any pair separates is proportional to the distance between them, and a straight line appears when that rate is plotted against distance. In the real cosmos, the grid is not a material sheet, and the rate is not fixed forever, but the nearby pattern behaves in that straightforward way. With a measured present Hubble parameter, astronomers can also form a simple timescale by inverting the rate as if the universe had always expanded at the same pace. This number is only a rough check because the true age depends on the full history of how the rate changes with time and composition. Still, the check is useful, and it has long served as a way to compare the current rate with ages inferred from the oldest stars and from the pattern of ancient radiation. In recent years, determinations of the present Hubble parameter made by different methods have shown mild tension with values inferred from the distance ladder, not fully matching values inferred from patterns in the ancient radiation. This puzzle motivates new measurements and careful tests for hidden biases, yet it does not unsettle the basic law at modest distances, which rests on direct pairings of distances with redshifts, and on the clear linear trend that emerges from those pairs. Most important for the theme of this script, the Hubble-Lemaitre law translates a set of spectral shifts and distances into a calm quantitative statement that large-scale separations grow because the metric that defines distance evolves with time. Nothing in the law asks for an outside region into which the universe expands. The measurements are self-contained. The light carries the record of stretching along its path, and the straight line states the present rate at which that stretching changes distances today. Later sections can describe the geometry that underlies this behavior, but the essential observational fact is already in view a near-linear relation at modest ranges that quietly points to an expanding space-time, rather than to objects flying outward through a fixed and empty stage. A simple language for the expansion of the universe begins with a statement about how space looks when viewed on very large scales. When many galaxies are averaged over volumes far larger than clusters, the distribution appears nearly uniform from place to place, and nearly the same in every direction. This large-scale sameness is called homogeneity and isotropy. It is an observation as much as an assumption, because maps of galaxies and of the ancient light that fills space show only small departures from smoothness at the biggest scales we can see. When these symmetries are taken seriously, they guide the form of the geometry that best describes the universe. Mathematicians and physicists call this description the Friedmann-Lemaitre-Robertson-Walker metric. The name marks the work of several early 20th century scientists who found all the ways a smooth, uniform and directionless space can expand or contract in time while remaining consistent with the rules of general relativity. In ordinary words, a metric is a rulebook for measuring distances and times. In daily life, rulers and clocks serve as measuring tools. In cosmology, the metric plays that role by telling how much distance lies between two places when the measurement is made at the same cosmic time and how much time elapses between two events. The form used for a uniform and directionless universe contains a single time-dependent function called the scale factor that multiplies spatial distances. When the scale factor grows, distances measured between co-moving points grow in the same proportion. Co-moving points are locations that ride with the large-scale flow without drifting through space under local forces. A galaxy that is not bound tightly to neighbours is a near example of a co-moving point. The scale factor says nothing about what a galaxy does within its own halo of dark matter or inside a group where gravity binds neighbours. It only states how the underlying measuring grid stretches with time. The metric also includes a number that encodes the spatial curvature of the universe. There are three broad possibilities. Space can be exactly flat, in which case large triangles have interior angles that add up to straight lines, and parallel lines remain parallel when extended across vast distances. Space can be positively curved, which loosely resembles the geometry on the surface of a sphere, where great circles that start out parallel eventually cross. Space can be negatively curved, which is sometimes compared to a saddle shape, where lines that start parallel spread apart. These pictures are analogies for understanding and not literal embeddings in a higher space. The metric does not require that our space sit inside a larger space. It only carries the internal rules that distances and angles obey within our own three-dimensional world. The curvature choice and the scale factor together fix how distances should be measured as the universe evolves from one cosmic time to the next. Cosmic time here means the time measured by clocks carried by co-moving observers who see the universe as statistically the same in every direction. In practical work, astronomers use the redshift of light as a stand-in for cosmic time, because a larger redshift usually means the light left its source when the scale factor was smaller and the universe was younger. The strength of this metric framework is that it compresses the largest features of the cosmos into a small list of functions and numbers that observations can measure. One set of observations maps the small temperature patterns in the ancient glow that fills space. Those patterns carry the imprint of geometry and of the scale factor at the time when the glow last scattered from matter. Another set of observations traces the gentle ripples in the distribution of galaxies that were seeded in the early plasma and later grew into a cosmic web. The spacing of those ripples today acts as a standard ruler that records how the scale factor has changed with time. Supernova distances at many redshifts record the way the scale factor accelerates or decelerates at later epochs. When all of these are compared to the metric description, the numbers that define curvature and the time history of the scale factor can be inferred. In this language, there is no need to imagine space as a material sheet that inflates into an outside room. The metric supplies all distances internally. An observer in any ordinary galaxy can choose co-moving coordinates that label each galaxy by fixed spatial markers, like addresses that drift only because the measuring standard stretches. The addresses themselves do not move through space. Rather, the way distance is computed between two addresses changes with cosmic time. This viewpoint also clarifies why there is no global center of expansion. Because the metric is the same at every co-moving location on large scales, each typical observer sees distant galaxies recede in a nearly symmetric pattern. If two such observers exchanged their data, each would find that the other lives in a cosmos described by the same rulebook with the same growth of the scale factor at the same era. Local differences, such as being inside a small group or near a cluster, are small ripples on top of the common flow. The Friedmann-Lemaitre-Robertson-Walker metric arises from general relativity with matter and radiation as sources of gravity. When the contents of the universe are specified in broad categories such as radiation, ordinary matter, dark matter, and the energy that drives late-time acceleration, the equations link those contents to the time evolution of the scale factor. In words more, matter and radiation try to slow the growth by their gravity, while the late-time energy acts with negative effective pressure and tends to speed the growth. By fitting the metric model to many independent observations, one learns how these influences balance through cosmic history. The scale factor at any chosen time then tells the physical distance between co-moving points, at that time the path of light between emission and observation, and the relationship between redshift and cosmic time. This language explains familiar expansion statements with precision. When a distant galaxy shows a certain redshift, that shift is not a Doppler effect caused by the galaxy ploughing through space in the usual sense. It is primarily the stretching of the wavelength as the scale factor grows along the photon's path. When the galaxy is farther away, the photon spends more time in transit and experiences more growth of the scale, so the shift is larger. When many galaxies are measured, the pattern of shifts against distance reveals the present rate of growth of the scale factor, and at larger ranges the way that rate changes with time. The metric also clarifies what superluminal recession means. There is no law in relativity that limits the rate at which the metric can assign increasing separation to widely separated co-moving points. The light speed limit applies to motion through space, not to the rate at which the measuring grid stretches. Thus, very distant galaxies can recede from one another faster than light by this definition, without breaking relativity, and their light can still reach us if it was emitted when the growth of the scale allowed the path to shrink inside our observable horizon. The precision of the metric description does not remove open questions. The global shape of space could be exactly flat or only nearly flat within the visible region. The topology of space could allow a finite volume without edges, or it could extend without limit. These possibilities leave subtle signatures in the pattern of the ancient glow and in the statistics of large structures, and current dia place tight bounds without yet closing every door. Still within the region we can observe the metric with a smoothly growing scale factor, and near-zero curvature gives an excellent account of the data. Most important for the central question of this script, the metric formalism makes it clear that expansion is not a movement into an outer space. Distance is a relation defined by the metric inside the universe itself. When the scale factor grows, those relations change everywhere at once in a way that respects the large-scale uniformity. No boundary is required, no outside stage is needed. The rulebook that defines distance and time is sufficient to describe how galaxies separate how light stretches, and how the history of that stretching is read from the sky. Co-moving coordinates offer a quiet way to think about expansion that removes unnecessary motion, and leaves only the slow drift that the metric prescribes. A coordinate is simply a label for position. In daily life, a street address does not move with a person, but in cosmology, it is useful to assign addresses that ride along with the large-scale flow. A co-moving coordinate marks a location that remains fixed with respect to the uniform distribution of matter when averaged over very large volumes. A galaxy that is not under the strong pull of neighbours and that follows the general expansion is well approximated by such a co-moving marker. In this language, the distance between two co-moving points changes because the scale factor changes, not because either point slides across a background. The coordinate addresses remain the same, while the rule for converting address separation into physical distance evolves smoothly with cosmic time. This viewpoint explains why an observer in an ordinary galaxy can consider herself at rest with respect to the large-scale universe, and still see distant galaxies recede. Rest here means no local drift through space, beyond small motions caused by nearby structures. The observer carries a clock and a ruler. At one cosmic time she measures the distance to a distant co-moving galaxy and writes down the result. At a later cosmic time she repeats the measurement using the same procedure and finds a larger distance. The co-moving coordinates of both locations have not changed, yet the measured separation has grown, because the scale factor that multiplies those coordinates has grown. The words stillness and drift can be confusing if left undefined. A clear separation helps. Peculiar motion is the motion of an object relative to the co-moving grid. It arises when local gravity from a cluster, a group or a nearby neighbour accelerates the object. A galaxy that orbits inside a cluster shows peculiar motion. A star that orbits within a galaxy shows peculiar motion. These motions are real and measurable, and they leave small Doppler contributions in spectra, along with the stretching produced by the expansion. Yet when distances become large, these local motions are small compared with the change driven by the scale factor. The co-moving grid, in contrast, is not a material net that exerts forces. It is the set of coordinate labels for which the metric takes the simple, uniform form of the Friedman-Lemaitre-Robertson-Walker description. In these coordinates, freely falling particles that are not bound to neighbours follow co-moving world lines. They keep the same spatial labels while their physical separations grow in step with the scale factor. This is what is meant by stillness in an expanding universe. The physics of light fits this picture in a consistent way. A photon leaves one co-moving location with a certain wavelength. As it travels, the scale factor grows and the wavelength grows with it. When the photon arrives at the observer, the longer wavelength records the integrated growth that happened while it was in flight. No extra motion through space is required to explain the change. The co-moving coordinate of the emitting galaxy may be the same at emission and at observation, and the change in the photon tells the whole story of how the scale has evolved along the path. A practical advantage of co-moving coordinates is that they allow simple statements about conservation on large scales. The density of matter in co-moving volumes changes as the scale factor changes, because the same amount of matter occupies a larger physical volume as the universe grows. The average density declines in a predictable way for matter and for radiation, while the effective energy that drives late-time acceleration remains nearly constant in physical units in the standard model. These statements are compact and clear in co-moving language where volumes scale with the cube of the scale factor and wavelengths scale linearly with the scale factor. The stillness of co-moving points also clarifies why small systems do not expand. Within a galaxy, gravity binds stars into orbits that change slowly over many rotations. Within the solar system, planets remain in nearly the same paths around the Sun. The co-moving description does not claim that every separation grows. It applies where the average cosmic mass distribution can be treated as smooth and where local binding forces do not dominate. On those larger scales, the co-moving grid is an accurate description, and the change of the scale factor governs measured distances. The tension many people feel about expansion often comes from mixing these two regimes. They imagine an entire galaxy or a laboratory bench being stretched by the same factor that acts between clusters. The correct statement is more modest. The metric that defines distance grows on very large scales. Local systems are held together by forces that set their own sizes, and those sizes are not altered by the gentle background growth. A step-by-step thought experiment makes the point. Imagine two small spacecraft drifting in intergalactic space far from clusters initially at rest, with respect to the co-moving grid and separated by a measured distance. In the absence of propulsion and local binding, their co-moving coordinates do not change. At later times, their physical separation is larger in exact proportion to the growth of the scale factor. If small thrusters fire to hold their separation fixed in physical units, the craft acquire a slight peculiar motion inward relative to the co-moving grid. If the thrusters fire in the outward direction to increase the separation faster than the scale factor, the craft acquire a peculiar motion outward. Co-moving stillness is therefore a specific physical state, not a philosophical statement. It has measurable consequences for energy requirements and for how light beams exchanged between the craft evolve in wavelength. The mathematics behind this picture flows from the geodesic equations of general relativity specialized to a homogeneous and isotropic spacetime. A freely falling test particle with no peculiar velocity remains at fixed co-moving coordinates, while its proper distance to any other such particle grows with the scale factor. The same formalism shows that peculiar velocities decay with time, as the universe expands when no forces replenish them, because the kinetic energy associated with small drifts redshifts away just as photon energies do. This decay offers another sense in which co-moving stillness is natural at late times on large scales. Regions that are not bound slowly shed their small relative motions and settle into the general flow described by the expanding metric. The notion of a preferred rest frame appears within this context in a subtle but observationally grounded way. The ancient radiation that fills space has a nearly uniform temperature in every direction for an observer who is at rest with respect to the co-moving grid. If an observer moves with a peculiar velocity, the radiation appears slightly warmer in the direction of motion and slightly cooler in the opposite direction. By measuring this dipole pattern and removing it, observers define a frame that is as close as possible to the co-moving rest frame in our region. This practice is not a violation of relativity. It is a practical way to tie measurements to the large-scale flow described by the metric. It shows that co-moving stillness is not only a useful idea, but one that can be approached in real observations. The concept also removes the need to ask what the universe expands into. When distances are relations defined by the metric inside the universe, and when co-moving coordinates track those relations without invoking motion, through an outside stage the expansion becomes a change of those internal relations alone. There is no boundary that moves outward, and no exterior room that receives the expansion. The co-moving grid fills space by definition, and its properties evolve through the scale factor. The light that crosses it stretches with the same factor. The matter that rides with it spreads into larger volumes as the factor grows. The role of co-moving coordinates is to keep the bookkeeping tidy and to make clear which motions are real local drifts and which are only the gentle widening of space itself. In later sections, the geometry and the energy content that drive the time evolution of the scale factor can be discussed in more detail. For now, the essential point stands. A calm description of the universe treats widely separated galaxies as nearly still in co-moving coordinates. Their separations increase because the cosmic rule for measuring distance changes with time. This rule is written by the metric. It is read in the redshifts of light. It is confirmed by the way small peculiar motions fade on very large scales. Under this rule, the cosmos needs no outside realm. It carries its own coordinates, its own clock, and its own steadily growing measure of distance within the same self-contained space-time. Curvature and geometry enter the story when one asks how straight lines behave, and how shapes measure up on the largest possible stage. In ordinary experience, triangles drawn on a flat table have interior angles that add to a straight angle, and parallel lines remain everywhere the same distance apart. On a sphere, the rules are different. Take two lines of constant longitude on a globe. They begin parallel at the equator, yet they meet at the pole. A triangle traced by those lines and a segment of the equator can have interior angles that add to more than a straight angle. On a saddle-like surface, lines that begin parallel drift apart, and a large triangle has interior angles that add to less than a straight angle. These examples are not meant to say that space lives inside a larger room with tables, spheres, and saddles. They serve only to fix ideas. What matters is that the rules of distance and angle can differ from place to place in ways that are captured by curvature. Cosmology asks about the average curvature of space when matter is smoothed over very large regions. The Friedman-Lemaitre-Robertson-Walker description offers three broad possibilities. Space can be exactly flat in the average, so that the familiar rules hold on the largest scales. Space can be positively curved in the average, loosely echoing the behavior of a sphere, where straightest possible lines eventually meet, and the volume contained within a fixed radius comes out smaller than it would in flat space. Space can be negatively curved in the average, echoing the saddle behavior, where straightest lines diverge and the volume contained within a fixed radius exceeds the flat space value. A convenient way to think about this without drawings is to imagine placing circles of increasing radius around a point and measuring their circumferences and the volumes they enclose. If the circumference grows exactly in step with the rules of flat geometry, and if the volume matches the flat space expectation, the space is flat. If both numbers are smaller than flat expectations, the space carries positive curvature. If both numbers are larger, the space carries negative curvature. The metric that governs the cosmos in this framework allows one number to encode which of the three cases applies, and observations can constrain that number. Curvature in cosmology refers to the shape of the spatial slices taken at a single cosmic time after averaging over large regions. It does not refer to the common warping of space-time around stars and galaxies caused by local mass. Local warps produce gravitational lensing and orbit precession within galaxies. Global spatial curvature asks a different question. If one could ignore local lumps and measure great triangles that span billions of light years, how would their angles add up, and how would volumes and distances compare to those of a perfectly flat space? The ancient radiation that fills space helps to answer this question. At the time when light last scattered from the early plasma, there is a characteristic physical scale imprinted in the pattern of temperature variations on the sky. It arises from sound waves that travel a certain distance before scattering ends. That physical distance exists as a standard ruler on the last scattering surface. When observers measure the typical angular size of that ruler today, the result depends on the geometry of space between that ancient surface and the present. In flat space, the angular size takes one value. In positively curved space, angles are magnified, and the same physical size appears larger on the sky. In negatively curved space, angles are reduced, and the same physical size appears smaller. Detailed maps of the cosmic microwave background compare the measured angular pattern to predictions and thereby infer whether the average geometry is flat or curved. A similar logic applies to gentle ripples in the distribution of galaxies known as baryon acoustic oscillations. These ripples reflect the same physical process that leaves its mark on the ancient glow. Their preferred separation acts as a standard ruler that can be measured at later cosmic times. When surveys count galaxy pairs as a function of separation across wide volumes, they see a small preference for a certain comoving scale. The angle and the redshift separation that correspond to that physical scale at a given time depend on the geometry and on the expansion history. By comparing the observed pattern with the model predictions, one can test curvature while also tracing the growth of the scale factor. Supernova distances and gravitational lensing statistics add complementary information by measuring how light travels and how volumes grow as a function of redshift. Together, these probes show that the large-scale geometry within the observable region is very close to flat, with any deviation constrained to be small. The phrase very close means that within the precision of current data triangles that span the observable cosmos have sums of interior angles so near a straight angle that no difference can be confirmed. This conclusion does not mean that curvature is exactly zero. It means that if there is a non-zero average curvature, it must be small enough that the imprints on these rulers and rulers at many redshifts fall within the measured uncertainties. Curvature also influences how the past and the future are described, but only through geometry, not through edges. In a positively curved universe, one can have a finite spatial volume without any boundary. A traveller who moves always in a single direction could return to the starting location, just as a traveller on Earth returns after a long journey along a great circle. In a negatively curved or flat universe, space can extend without limit while still lacking an edge. These statements concern only spatial geometry at one time slice, and do not assert that such journeys are practical or possible within a lifetime. They express how the measuring rules join up globally. It is important to separate curvature from expansion. The scale factor tells how distances change with time. Curvature tells how distances and angles relate across space at a given time. A universe can expand while being flat open or closed. The rate of expansion and the way that rate changes depend on the contents of the universe, such as matter radiation, and the energy that drives late-time acceleration. The average spatial curvature, in contrast, summarizes the shape of the cosmic stage on which this time evolution plays out. Observations indicate a stage that is remarkably close to flat, and they do so by reading the angles of ancient rulers and the separations of galaxies with great care. The conclusion that the stage is nearly flat within the observable region carries a practical message for the central question of this script. If space were expanding into a larger outside space, the measured rules for distance and angle would still be determined by the internal metric, and the presence of an outside room would add nothing to the observed relationships. All of the quantities just described depend only on the path that light takes within the universe and on the internal geometry along that path. The nearly flat result arises from internal comparisons between physical rulers and their observed angles and separations. No appeal to an exterior stage is necessary or helpful. The mathematical formalism that connects curvature to observable angles does not require embedding in a higher space. It requires only that distances and angles be defined by the metric of our own space-time, and that matter and radiation follow the paths that this metric prescribes. When this perspective is kept, the tests of curvature become straightforward. They reduce to reading the sky with calibrated rulers and clocks, and comparing the readings to the three possibilities that homogeneity and isotropy allow. The data say that the observable region is very close to flat. The next task, taken up in later sections, is to ask about the global shape beyond the observable part, a question that belongs to topology rather than to curvature. For the present section, the calm conclusion is that the large-scale geometry measured within our horizon matches the rules of flat space to high precision, while leaving room for tiny departures that future surveys may measure, all within a description that treats expansion as the evolution of the internal metric rather than as motion into any exterior room. Topology and boundaries enter the story when one asks how space can join to itself or extend without limit while keeping the same local geometry from place to place. Curvature describes the local rules for angles and distances on a single time slice. Topology describes how the whole of space is connected globally. A familiar example helps to fix ideas without suggesting an external room. Consider a flat sheet that is imagined to join its left edge to its right edge and its top edge to its bottom edge. The resulting space is finite in area, yet has no boundary within the sheet itself. A traveller who moves in a straight line eventually returns to the starting point, and every local patch looks flat. This is an example of a multiply connected space with zero curvature. The same idea can be extended to 3 dimensions. A 3-dimensional space that joins opposite faces of a box with matching rules is called a 3-dimensional torus. It is finite in volume and lacks edges while remaining locally flat. Similar constructions exist for positively curved and negatively curved geometries. The global shape that results is called the topology. Importantly, topology does not change the local law that defines how rulers and protractors behave. It only changes how distant regions are identified with one another. Cosmology asks whether the global topology of our universe could be finite without boundary, or effectively infinite, and whether multiple images of the same region might appear across the sky, because light can take different wrapped paths through a multiply connected space. Observations approach this question in several ways. The ancient radiation that fills space offers a particularly sensitive test. At the time when light last scattered from matter, the surface from which that light originates forms a nearly spherical shell around each observer. If space has a multiply-connected topology with a fundamental domain smaller than that shell, then the shell can intersect itself in such a way that matching circles with the same pattern of temperature variations appear at different places on the sky. This is the circles in the sky method. By scanning the full sky maps of the ancient radiation for pairs of circles, with identical patterns one can test for certain classes of topologies and constrain the minimum size of the fundamental domain. Extensive searches have not found convincing matched circles above the noise level, which places lower bounds on the size of many candidate topologies. Another clue lies in the statistical power on the largest angular scales of the ancient radiation. Some simple multiply-connected models predict a suppression of correlations at very large angles, because wavelengths longer than the size of the fundamental domain cannot fit. The observed large angle power is low compared with some expectations of simple models, but the significance of that feature is debated because cosmic variance is large on those scales, and because foreground removal and instrument systematics complicate the analysis. As a result, while the data allow constraints on specific compact topologies, they do not yet provide an unambiguous detection. Galaxy surveys and three-dimensional maps offer complementary tests. If space repeats in a wrapped way, then widely separated regions could show repeating patterns in the positions of galaxies or in the distribution of clusters when measured in comoving coordinates. Searches for periodicity or for repeating spatial motifs have been carried out, but the growth of structure and the limitations of survey depth and selection make such signals subtle. Current surveys generally find no strong evidence for repeating patterns that would signal a small fundamental domain. Gravitational lensing provides another angle. In a multiply-connected spacelight from the same source could reach the observer along different topological paths that are not caused by local mass concentrations. This would generate multiple images with specific separations and redshift relations beyond those expected from lensing by galaxies and clusters. No clear examples of such topological lensing have been established, which again pushes the minimum size of many candidate topologies beyond the observable region, or at least beyond the sensitivity of current data. A concrete illustration of a finite without boundary model is the Poincaré dodecahedral space, which identifies opposite faces of a dodecahedron after a rotation. This model is positively curved and finite. It predicts specific patterns in the ancient radiation, including sets of matched circles with particular angular sizes and orientations. Searches for those signatures have not found the required matches at high confidence, leading to strong constraints on that model's parameters. The three-dimensional torus model is another often discussed case. It is locally flat and finite. It predicts matched circles and repeating patterns in galaxy distributions if the fundamental domain is smaller than the observable region. The absence of such clear signals in present data pushes the fundamental domain, if it exists, to be at least as large as the observable region, and likely larger. These examples show how topology and observation meet specific identifications lead to testable sky patterns. The difference between curvature and topology bears repeating. A space can be globally flat and finite like the three-dimensional torus, or globally flat and infinite like ordinary Euclidean space. A space can be positively curved and finite without edge like the three-dimensional analogue of the sphere, or it can be negatively curved and either finite or effectively infinite depending on identifications. Curvature governs the relation between angles and distances locally. Topology governs how the space is connected globally. The observable universe is the region from which light has had time to arrive since the hot early phase. If the global topology has a scale larger than this region, then no present observation can reveal the full shape, and the universe appears simply connected within our horizon. If the topology scale is smaller, then some of the signatures just described could be present. Current measurements suggest that if spaces multiply connected, the fundamental domain is at least comparable to or larger than the observable region for many common models. That is a statement about what the data can currently exclude rather than a declaration of what must be true. It reminds that topology is a global property that may lie partly or wholly beyond present reach. The practical meaning for the central theme is straightforward. Whether space is simply connected or multiply connected, whether it is finite without boundary or extends without limit, expansion remains a change in the metric that defines distances inside the space. No external region is needed to host the growth. The metric assigns distances between co-moving points. The scale factor changes those assignments with time. If space wraps the assignments, repeat according to the identifications. If space does not wrap the assignments, extend smoothly without repetition. In neither case does an edge move outward into an exterior room. Tests of topology continue to improve as maps of the ancient radiation gain sensitivity, and as galaxy surveys cover larger volumes with better control of selection and calibration. Future work may tighten bounds or reveal subtle signatures. For the present, a calm summary is that the global shape remains an open question within strict limits. The local geometry is very nearly flat within our horizon, and the expansion is fully described by the internal metric independent of any outside construction. In this way, topology enriches the description of the universe without altering the essential fact that what expands is the measure of distance within space-time itself, rather than a boundary that advances into something beyond. The idea of an observable universe begins with the simple fact that light travels at a finite speed and that the cosmos has a finite age. When an observer looks outward in any direction, the view is a layered record of earlier times, because the light from each shell of distance has taken a measurable duration to arrive. The farther the shell, the older the scene. This time-layered view builds a sphere around the observer whose radius is set by how far light could have travelled, since the hot early phase when the first neutral atoms formed and the fog of scattering thinned. That radius is called the particle horizon, in the language of cosmology. It does not mark a wall in space, and it does not mark the edge of all that exists. It marks only the limit of what can be seen today, because no signal from beyond that sphere has had time to arrive. The shape of the sphere is defined by the same metric that governs all large-scale distances. If space is nearly flat within the region we can map, then the horizon has the simple geometry of a round shell, whose centre is wherever the observer stands. Every ordinary galaxy carries its own such sphere centred on itself, because the limit is set by light travel time and not by a global boundary. The interior of the sphere contains everything that has sent light or other signals that have reached the observer by the present cosmic time. The exterior contains regions that may be very similar to the interior or may differ in ways we cannot yet test. The existence of a horizon has several quiet but important consequences for how observations are interpreted. First, every sky map is a map of the past light cone, not a slice of the cosmos at one moment. A distant galaxy is seen as it was when the scale factor was smaller and when the matter around it was less clumped. The ancient glow that fills space is seen as it was when the hot plasma cooled enough for light to decouple from matter and stream freely. Second, the size of the observable sphere depends on the time history of the scale factor, because the path of light is stretched by the same expansion that separates galaxies. The largest comoving distance from which light could have reached us since the beginning is larger than one might guess by multiplying the age by the speed of light, because the stretching of space expands the path itself, while the light travels, allowing photons to arrive from regions that are now much farther away in physical distance than the simple product would suggest. Third, the horizon is not a sharp imaging limit but a boundary in principle. Light from just inside the horizon arrives very faint and very red, stretched far into long wavelengths as the scale factor grows along its path. Any practical observation is limited by detector sensitivity foreground emission and the transparency of matter along the path. In practice, the most distant light that carries a clear image is the ancient cosmic microwave background, which comes from a time when the universe first became transparent. No ordinary telescope can see a galaxy older than that, because before that time atoms have not formed, and light scatters repeatedly from free electrons erasing images. The ancient glow is therefore the last surface of image bearing light, and forms a smooth shell slightly inside the formal particle horizon. Because an observer sees only the interior of the sphere at the present time, it is vital to distinguish the observable universe from the whole universe. The whole may extend without limit, or it may close on itself in a finite volume without boundary, or it may have a more complex wrapped structure. The interior of the sphere provides only a sample. If the cosmos is statistically the same on very large scales, then the sample is likely representative. If there are global features on scales larger than the horizon, present instruments cannot detect them directly. This limitation is not a flaw in the theory of expansion. It is a recognition of what light can and cannot deliver in a finite time from great distances, while the measuring grid itself stretches. A second horizon appears when one asks a different question. The particle horizon answers what can be seen today. The event horizon answers what can ever be seen, even if one waits without limit. In an expanding universe that accelerates at late times, there exists a maximum comoving distance from which light emitted now can ever reach the observer in the infinite future. Regions beyond that event horizon are not merely unseen today. They are forever causally disconnected in the sense that no signal sent from them now will ever arrive. The existence and size of an event horizon depend on the detailed expansion history and on the energy that drives late-time acceleration. Observers infer the presence of that energy from supernova distances, from the pattern of the ancient glow, from the growth of structure, and from gravitational lensing. These inferences imply that the event horizon is a meaningful concept for our cosmos. It is, however, distinct from the particle horizon. One concerns the past, one concerns the future. Neither is a material surface. Both are boundaries traced by the paths that light can take through the evolving metric. Horizon ideas can mislead if they are pictured as shells that expand into some surrounding room. The particle horizon expands in the sense that more distant regions come into view as time passes, and as new shells of light arrive, yet the expansion here is not motion into an outside place. It is the simple fact that light has had more time to cross the internal geometry. The event horizon is not a shell that advances through space. It is the limit of future reach defined by the internal rules that light follows, in a metric whose scale factor changes according to the matter and energy within the universe. These horizons help clarify common questions. Some ask whether a very distant galaxy that today recedes faster than light can ever be seen. The answer depends on when the light was emitted and on the subsequent growth of the scale factor. Light emitted long ago from a region that was then within our past light cone can arrive, even if the source now recedes faster than light by the metric definition. In contrast, light emitted today from a source beyond the event horizon will never arrive. The difference rests entirely on the behavior of the scale factor through time, and does not require motion through a fixed external stage. The observable sphere also frames how cosmic homogeneity is tested, because the sphere is large maps of galaxy distributions of the ancient glow and of the weak lensing shear field, can be averaged over many directions to look for departures from uniformity. These tests show that after known foregrounds are removed, the larger scales we can observe are remarkably uniform with only tiny fluctuations that serve as seeds for later structure. The uniformity does not guarantee that regions beyond the horizon are the same. It tells only that within our observable domain the cosmos is smooth to a very high degree. The next generation of surveys aims to push these tests closer to the practical limits set by the horizon by mapping more of the sky to greater depths with better calibration. None of these efforts change the core meaning of the horizon. They deepen the record within the sphere. Finally, the idea of an observable sphere underscores the script's central theme. When one asks what the universe expands into, the horizons give a clear reply by example. All of the distances involved in defining the particle horizon and the event horizon, all of the redshifts and angles and time delays that mark their existence, are computed within the metric that belongs to the universe itself. The horizons are not where space meets an exterior void. They're where light paths end given the internal rules. The sphere grows with time because more light has time to arrive, not because a boundary pushes outward into a larger room. In this picture, the observer is always at the center of the observable sphere, not because the observer is special, but because the sphere is defined by what has reached that location by now. Every distant galaxy builds its own centered sphere, and the growth of each sphere is a quiet bookkeeping of light and time in a space-time whose scale factor evolves according to the matter and energy within. The cosmic microwave background presents a quiet all-sky glow that arrives from every direction, with a temperature just a few degrees above absolute zero when measured in long wavelengths of light. This glow is not a foreground from dust or gas in our galaxy. It is a relic of the time when the young universe first became transparent and light could travel freely without being scattered at every step. Before that time, matter exists as a hot, nearly uniform plasma of free electrons and atomic nuclei. Photons scatter again and again from the electrons and cannot stream across long distances. As the universe expands and cools, electrons combine with nuclei to form neutral atoms. The scattering thins and a sea of photons decouples from matter and begins a long journey through the growing cosmos. Those photons reach present instruments as the cosmic microwave background. The remarkable feature of this glow is its spectrum. When measured with high precision, the spectrum follows the shape expected for light from a body in perfect thermal equilibrium at a single temperature. No known process in the nearby universe can produce such a nearly perfect thermal spectrum across the entire sky. This one observation already points to a hot early phase in which matter and radiation share a common temperature before decoupling. The near perfection of the spectrum also confirms that the expansion stretches wavelengths without distorting the overall thermal shape. As the scale factor grows, each photon's wavelength grows in proportion, the temperature drops in the same proportion, and the distribution of light remains thermal. The uniformity of the glow is striking but not absolute. After subtracting the dipole pattern that arises from the small peculiar motion of the solar system, with respect to the large-scale rest frame maps, reveal temperature variations that are only a few parts in 100,000. These tiny ripples are the seeds from which later galaxies and clusters grow. Their statistical properties carry a detailed record of conditions in the early plasma, and of the geometry through which the photons have travelled. The pattern is not random noise. It shows acoustic peaks at specific angular scales which arise from sound waves that compress and rarefy the plasma before decoupling. Where a region has just reached maximum compression or rarefaction, at the moment of a last scattering, the temperature contrast becomes larger or smaller. The typical angular size of the first peak corresponds to the distance a sound wave can travel in the plasma before decoupling projected onto the sky through the intervening geometry. Because that physical distance is known from the physics of the plasma, the observed angular scale serves as a sensitive measure of spatial curvature within the observable region. A peak at the scale predicted for flat geometry supports the conclusion that space is very nearly flat on large scales, while any systematic shift would indicate positive or negative curvature. The heights and spacings of the peaks tell more. They depend on the densities of ordinary matter and of the dark matter that does not interact with light, because those densities set how the plasma oscillates and how gravity and pressure balance at the time of decoupling. By fitting the pattern with models of a homogeneous and isotropic universe, observers infer the proportions of matter and radiation, the present rate of expansion, and the amplitude and tilt of the initial fluctuations that seed later structure. The polarization of the cosmic microwave background adds a second independent window. When light scatters from electrons, it becomes polarized in a manner that depends on the quadrupole pattern of light at the scattering location. The early plasma contains such patterns because of the same acoustic motions that create temperature ripples. As a result, the last scattering surface imprints a specific polarization field on the sky. The even parity component of this field aligns with expectations from scalar or density fluctuations, and its angular power spectrum shows peaks that echo the temperature peaks in a shifted pattern. Measuring this polarization confirms the acoustic picture and strengthens the inference that the ripples arise from primordial density variations in a nearly uniform plasma. The odd parity component of polarization would carry signatures from different sources, and searches for such signals continue with improving sensitivity. Light from the cosmic microwave background also picks up new information as it passes through later structures. Slight gravitational lensing by the large-scale distribution of matter blurs and distorts the pattern in a predictable way. By measuring this lensing effect, observers reconstruct a map of the integrated mass distribution between the last scattering surface and the present. This reconstruction helps to track the growth of structure and to compare it with predictions from the same model that fits the acoustic peaks. In addition, when the expansion rate changes with time under the influence of late-time acceleration, the gravitational potentials associated with large structures evolve and imprint a small additional correlation between the temperature pattern and the distribution of galaxies, an effect known as the integrated Sachs-Wolf signal. Detecting and measuring this correlation provides yet another check on the expansion history and on the presence of energy that act with negative effective pressure. The progress from first detection to detailed mapping has been steady and cumulative. Early balloon experiments and ground-based instruments established the existence of ripples. A satellite in the 1990s measured the near-perfect thermal spectrum and detected large-scale anisotropy. A later spacecraft mapped the sky at finer resolution and confirmed the acoustic peak structure. The European Space Agency Planck mission delivered even sharper maps of temperature and polarization and measured the lensing signal with high significance. These steps taken together transform the cosmic microwave background from a discovery into a precision tool. They fit to a simple, nearly flat model with cold dark matter and a component that drives late-time acceleration, is not an assumption imposed on the data. It is a result that emerges when many features are matched at once: the angular location of the first peak, the relative heights of the first several peaks, the shape of the polarization power, the lensing deflection field, and correlations with the distribution of nearby matter. Alternative ideas must reproduce this full suite of observations with the same economy to be plausible. The cosmic microwave background also clarifies what expansion means. The uniform thermal spectrum today at long wavelengths implies an origin at much higher temperature and shorter wavelengths, made cool by the stretching of space itself rather than by dilution in a fixed room. The small ripples show that the early universe is not exactly uniform, and the pattern of those ripples shows that gravity and pressure have time to set up standing waves before light decouples. This story requires a long, smooth evolution of the scale factor from a hot, dense state to a cool, transparent one. It does not require motion into an exterior space. All distances, times, and angles needed to explain the glow, and its pattern are computed within the internal metric. Even the tiny deviations from uniformity acquire their meaning from the same rulebook. The photons remember the growth of the scale factor along their entire paths, and their wavelengths and angles carry that record to present detectors. The glow is sometimes pictured as a surface, yet this surface is not a wall. It is a shell in time defined by when scattering ends along each line of sight. Behind it in look back time lies a plasma where images cannot form. In front of it lies all of later cosmic history, through which the photons pass, acquiring lensing deflections and subtle shift when potentials evolve. The fact that instruments can measure so many of these subtle marks is a testament to stability and calibration, but the marks themselves are set by physics and by geometry rather than by any outer frame. For the theme at hand, the conclusion is simple and direct. The cosmic microwave background is a powerful, quiet proof that expansion is a change within spacetime. Its spectrum demonstrates cooling by metric stretching. Its anisotropies and polarization encode sound waves in a young plasma, and the geometry of the path from then to now. Its lensing and late-time correlations trace the growth of structure and the influence of the energy that speeds the expansion at recent times. None of these facts point to an edge that moves into an outside region. They point instead to a self-contained history in which the rule for measuring distance evolves, the light stretches with it, and the sky preserves that evolution as a faint, nearly uniform afterglow that surrounds every observer in every ordinary galaxy. Standard rulers in cosmology are physical scales whose sizes are set by well-understood processes, and that persist as quiet markers across time, letting the expansion history be read from how large those markers appear at different redshifts. Among these rulers, baryon acoustic oscillations provide a particularly clear and durable measure. In the hot early plasma of light and matter, small variations in density excite waves that travel outward as alternating regions of compression and rarefaction. Pressure from light pushes outward while gravity and the inertia of ordinary matter pull inward, so a sound speed arises that is a fixed fraction of the speed of light set by the conditions of the plasma. These waves propagate until the epoch when scattering of light from free electrons ends and atoms form. At that moment, the waves stop leaving a faint preference for matter to be separated by the distance the wave crests have reached. That distance is called the sound horizon. It is a physical length measured in comoving coordinates, which means it stretches with the scale factor after it forms. Because the physics of the early plasma is simple and well constrained by the pattern of the ancient glow, the size of the sound horizon can be calculated with high precision. The imprint of this scale is subtle but widespread. It appears as a slight excess of galaxy pairs separated by about 150 megaparsecs in co-moving distance, and it appears as gentle undulations in the spectrum of clustering strength as a function of scale. No single galaxy knows this scale, but the statistical pattern across millions of galaxies reveals it. Galaxy redshift surveys are designed to capture this pattern. They map positions on the sky and measure redshifts to place each galaxy along the line of sight. With those three-dimensional positions in hand, observers count galaxy pairs separated by different distances and look for a small bump at the sound horizon scale in the two-point correlation function. They also analyze the same information as a power spectrum in which the baryon acoustic feature appears as a series of broad wiggles. Because the feature is weak, large volumes and careful control of calibration are essential. When the signal is measured at several redshifts, it becomes a ruler that can be laid down at many times in cosmic history. The ruler gives two complementary kinds of distance information. Across the sky, the ruler's known physical size projects to an angular scale that determines the angular diameter distance at a given redshift. Along the line of sight, the same known physical size projects to a redshift separation that determines the expansion rate at that redshift. Modern analyses measure the angular and radial parts together and report a pair of numbers that say how large the universe is across and how quickly it grows at that epoch. The calculation of the ruler's physical length is anchored by the same early universe physics that sets the acoustic peaks in the cosmic microwave background. The temperature and polarization patterns of the ancient glow fix the mixture of ordinary matter, dark matter, and radiation, and they fix the sound speed and the time available for waves to travel before scattering ends. As a result, the sound horizon length is not an adjustable knob chosen to fit the galaxy data. It is predicted by the same model that matches the ancient glow and the galaxy maps. Then test whether the late-time geometry and growth are consistent with that prediction. The agreement found across many surveys and methods is a central pillar of modern cosmology. Late-time gravitational growth blurs the pristine ruler. As structures form, flows pull galaxies toward dense regions and push them from voids, and small random motions inside halos smear out the feature. A method called reconstruction uses the observed density field to estimate these bulk flows and to move galaxies partway back toward their initial co-moving positions. Reconstruction sharpens the baryon acoustic bump and increases the precision of distance measurements. In addition, observed redshifts include not only the smooth shift from expansion, but also small Doppler contributions from local motions which make clustering appear squashed or stretched along the line of sight. This pattern, known as redshift space distortion, is not noise to be discarded. It is a separate signal that measures how quickly structures grow. By modelling redshift space distortions together with the baryon, acoustic ruler observers extract both geometry and growth, creating a stronger test of the underlying model. Different traces extend the ruler across time. Bright galaxies map the nearby and intermediate universe. Emission line galaxies, selected for strong features that make redshifts easy to measure, push the ruler to earlier epochs. Quasars add reach to even higher redshifts. The hydrogen Lyman alpha forest, seen as a thicket of absorption lines in the spectra of very distant quasars, traces the structure of diffuse gas and carries the same preferred separation. By cross-correlating many lines of sight, the baryon acoustic feature emerges in the forest at redshifts well beyond those reached by galaxies alone. Together, these traces let analysts measure the ruler from roughly half the present age of the universe back to a time only a few billion years after the hot early phase. radio surveys promise a complementary map by detecting the faint emission from neutral hydrogen spread across vast volumes. Rather than detecting individual galaxies, these experiments measure intensity fluctuations in coarse voxels that retain the baryon acoustic signal. If successful, such maps will cover huge regions quickly and trace the ruler over an even broader range of times. Cross-correlations between these radio maps, optical galaxy maps, and reconstructed lensing of the ancient glow reduce systematic uncertainties and tie distance and mass information together in a single web. The baryon acoustic ruler complements standard candles such as Type 1 supernovae. Candles infer distance from brightness, while rulers infer distance from size. When both are plotted against redshift, they must agree on the same geometry for a single model to be viable. Observations show that a nearly flat model with matter and an energy component that drives late-time acceleration matches both kinds of data along with the pattern of the ancient glow and the measured lensing deflections. The point is not that a particular label is preferred for the energy that accelerates the expansion, but that its gravitational effect on distances and on structure growth is measured by multiple independent tools that converge. A separate geometric check known as the Alcock-Paczynski test uses the fact that an intrinsically spherical structure will appear distorted if the assumed conversion between angles, redshifts, and distances is wrong. By comparing clustering shapes in the angular and radial directions, one can solve for the combination of distances and expansion rates that makes the shapes come out round on average. When applied to large surveys, this test provides an additional constraint that aligns with the distances inferred from the baryon acoustic ruler. The practical meaning for the theme of this script is direct. The standard ruler is defined and measured entirely within the spacetime of the universe. Its physical length arises from processes in the early plasma that are described by the internal metric. Its apparent size and redshift thickness at later times are read along light paths that follow the same metric. No external stage is invoked or required. When the ruler appears larger or smaller, it is because the internal distances between comoving points have changed according to the scale factor, not because a boundary has moved through some outside region. The ruler's reliability rests on three qualities that are all internal. First, it is simple, tied to sound waves travelling at a known speed for a known time. Second, it is preserved because once set in co-moving units, it rides with the expansion and survives the later formation of structure, with only mild blurring that can be modelled and partly undone. Third, it is redundant, appearing in galaxies, quasars, diffuse gas, and in correlations with lensing so that no single data set controls the conclusion. When these lines of evidence are placed together, the distances across cosmic time trace a smooth curve that records the evolution of the scale factor and confirms late-time acceleration. In this way, baryon acoustic oscillations and other standard rulers translate the expanding metric into directly measured sizes on the sky, strengthening the calm answer that expansion is a change in internal geometry rather than motion into an exterior room. Inflation refers to a very early era in which the scale factor accelerates sharply for a short interval stretching space by an enormous factor in an extremely small time. The purpose of this mechanism is practical. It explains how the observable cosmos can be so uniform on the larger scales, why the measured geometry within the horizon is so close to flat, and how tiny initial seeds arise from which galaxies and clusters later grow. The first issue is uniformity. The ancient cosmic microwave background shows nearly the same temperature and directions that, without an early rapid stretch, would never have had time to exchange light or heat. Inflation resolves this by taking a small, nearly uniform region that already sits in mutual contact and widening it so greatly that it becomes the entire observable domain. The second issue is flatness. In a universe that expands without such an episode, even a small amount of spatial curvature tends to become more important over time. During accelerated expansion, the curvature term in the large-scale geometry is driven toward insignificance within the region that later becomes observable, so that triangles spanning the sky add their angles to almost a straight angle. A third issue concerns unwanted relics in some particle physics pictures, which inflation dilutes to unobservably low densities by expanding volumes so quickly that any such relics are spread thin. The physical driver of inflation can be described in plain words. For a brief era, the overall energy density is dominated by something that behaves like a nearly constant energy, stored in a field that fills space. This energy has an effective pressure that is negative, and in general relativity, a sufficiently negative pressure causes the scale factor to accelerate. When this happens, the distance between widely separated co-moving points grows so rapidly that regions which were once close enough to share information are carried far apart. The co-moving Hubble radius, which is the distance scale that marks which regions can be in contact at a given time, shrinks during inflation. A patch that is initially within this radius is pulled far outside it, so that the uniform conditions of the early patch are imprinted across an enormous volume. Later, as the accelerated phase ends, the co-moving Hubble radius grows again, and those regions slowly come back into mutual contact as ordinary hot expansion proceeds. Inflation is not only a smoothing device, it also provides a natural origin for the tiny departures from exact uniformity that later grow into structure. Quantum fields that fill space carry minute random fluctuations. During accelerated expansion, the stretching is so swift that these microscopic ripples are pulled to cosmic scales. When a ripple is drawn beyond the co-moving Hubble radius, causal processes cannot erase it, and it freezes in as a classical pattern, slightly denser patches here, slightly thinner patches there. After inflation ends and the universe is hot and filled with ordinary matter, and radiation gravity amplifies these small imprints, the pattern predicted in this picture has clear hallmarks. It is nearly scale invariant, meaning that fluctuations have similar strength across a wide range of sizes with a gentle tilt. It is close to Gaussian, meaning that the fluctuations resemble random draws from a simple bell-shaped distribution with very small departures. It is largely adiabatic, meaning that all components of the cosmic fluid vary together rather than sloshing out of phase. These features match the detailed maps of temperature and polarization in the cosmic microwave background and the statistics of the galaxy distribution, where coherent acoustic peaks a slight tilt away from perfect scale invariance and tight limits on non-Gaussian behavior are all recorded. A further prediction is a faint background of long wavelength gravitational waves generated by the same stretching of quantum ripples now in the geometry itself. These waves would leave a distinctive curl-like signature in the polarization of the ancient radiation on large angular scales. Experiments on the ground, on balloons, and in space continue to improve their sensitivity to this pattern. The absence of a definitive detection so far translates into upper bounds on the energy scale of the accelerated era and on how steeply the driving field rolls down its potential. Those bounds already eliminate some simple versions of the mechanism while leaving a broad family of models consistent with the data. The end of inflation must be graceful. The energy that drives the accelerated expansion needs to transform into ordinary particles and radiation to begin the familiar hot phase. This transformation, called reheating, can proceed in a smooth, or in a more explosive way depending on the details of how the field that powers inflation couples to other fields. Although many microphysical models exist, observations mainly constrain the large-scale consequences, the near flatness, the spectrum and statistics of the primordial ripples, and the absence so far of the predicted polarization curl pattern. The exact identity of the field and the precise shape of its potential remain open, and the data guide theorists toward forms that reproduce the measured tilt and the low level of non-Gaussian features, because the accelerated phase creates superluminal recession. At very large separations in the metric sense, it is useful to state again that this does not violate relativity. The light speed limit governs motion through space, not the rate at which the measuring grid itself stretches. During inflation, distances between far comoving points increase faster than light times time, yet that is a statement about the changing metric, not about objects racing through a fixed background. Photons still follow the rules of space-time, and whether their paths can cross a given separation depends on how the scale factor behaves before and after the accelerated era. Inflation also informs the discussion of global shape without deciding it. By stretching any initial patch by a huge factor, inflation makes the observable region appear very close to flat, even if the global topology is more complex. If spaces multiply connected with a small fundamental size before inflation, the rapid growth can push that size far beyond the horizon, so that present instruments cannot see repeating patterns. If space begins simply connected, the stretching maintains that simplicity within the region we can map. In either case, the local near flatness and the uniformity of the cosmic microwave background are natural outcomes. The mechanism carries further consequences that observations examine with care. The phases of the initial ripples are predicted to be coherent, which leads to a series of acoustic peaks, with specific spacing and heights in the temperature-power spectrum of the ancient glow, and in the even parity polarization spectrum that pattern is measured. The lensing of that glow by the later growth of structure is predicted to deflect light by small correlated angles whose statistics can be reconstructed, and that reconstruction matches the amplitude of structure expected from the same initial seeds. The faint preference for a standard ruler in the galaxy distribution set by sound waves in the early plasma arises naturally from the same physics. These agreements are not imposed by hand. They come from a single simple narrative in which a brief period of accelerated expansion sets initial conditions. The picture is not free of open questions. Which field or combination of fields drives the process? How exactly does reheating occur? Does the mechanism begin once and end everywhere? Or do remote regions beyond our horizon continue to inflate, leading to a patchwork of domains with varying properties? Some of these ideas are speculative and may remain beyond direct test for now, but their existence does not change the core success that the measured sky records a nearly uniform cosmos, a near flat geometry, and a spectrum of initial ripples with the right character to grow into the web of galaxies that surveys map. For the central theme of this script, the conclusion follows directly. Inflation does not ask the universe to expand into anything. It operates entirely within space-time by altering the rule that assigns distances between comoving points. The rapid growth of the scale factor smooths, flattens, and seeds the observable region, and the evidence for that sequence lives in internal distances, angles, and spectra. The sky does not show a boundary pushing outward into an outside room. It shows the fingerprints of an early mechanism that changed the internal metric for a short time, and left calm, measurable marks that modern instruments read with growing precision. Superluminal recession sounds like a contradiction until the distinct meanings of motion in an expanding space-time are carefully separated. The rule that no object can pass a light beam applies to motion through space, measured in any local laboratory, where gravity is weak and the curvature of space-time can be neglected over small regions. In such local patches, special relativity rules, and nothing outruns light. The expansion of the universe, in contrast, is not a wind that pushes galaxies through a fixed background. It is a gradual change in the metric, the rule that assigns distances between co-moving points. Because this rule can change everywhere at once, widely separated co-moving points can find their physical separation increasing faster than the speed of light without either point crossing a local light beam. The speed of light remains the local speed limit, but the rate at which distance grows between faraway markers is not that speed. This distinction becomes clear when distance and speed are defined with care. Proper distance is the separation between two co-moving points measured at one shared cosmic time by laying down a chain of small local rulers through which no step violates relativity. The recession speed is the rate at which this proper distance changes, because the scale factor changes not because either galaxy is moving through space. At very large separations, the proper distance can increase by more than the speed of light per unit time, and that statement is just a description of what the metric prescribes. Nothing in it allows a signal to leap across space faster than light, because signals are still carried by photons that trace null paths governed by the same metric. A photon emitted from a distant galaxy begins by moving toward the observer through local space at the speed of light in the frame of the local plasma. At the same time, the scale factor grows, and the proper distance between the photon and the observer can initially increase, because the stretching of space is strong enough at very large separations to carry the two apart faster than the photon can reduce the gap. As cosmic time passes, the proportional rate of growth can decline, or the photon can cross into regions where the local expansion is less effective at increasing the gap. When this happens, the proper distance between photon and observer begins to shrink, and the photon eventually reaches the detector. This is why light from sources that now recede superluminarly can still arrive. The path depends on the full-time history of the scale factor, not on a single momentary comparison with the speed of light. A related concept is the Hubble sphere, defined as the distance at which the present recession speed equals the speed of light when one multiplies the present Hubble parameter by distance. The Hubble sphere is not a horizon. It is a marker where the present rate of metric growth matches the speed of light. Photons can cross inward through this sphere and later arrive because the sphere itself evolves as the Hubble parameter changes with time. By contrast, an event horizon, when it exists, is a true limit on future contact defined by the integral of the expansion history. Photons emitted today from beyond that limit never reach the observer in any future, yet photons emitted long ago from the same region can already be en route if the scale factor and the Hubble parameter had different values along their earlier paths. In this way, superluminal recession, Hubble spheres and horizons are distinct ideas tied together only by the changing metric. The spectral shift of light also reflects this difference between motion through space and the growth of space. In a nearby laboratory, a Doppler shift arises because a source moves through space toward or away from the observer. In an expanding universe, a large part of the redshift arises from the stretching of wavelength as the photon traverses a path during which the scale factor grows. For small separations and small redshifts, a Doppler description approximates the effect, but at large separations the cosmological redshift records the integrated expansion rather than a single relative speed through space. The same photon can be described as experiencing many tiny Doppler shifts as it crosses a chain of local comoving frames. Yet the operational meaning is that its wavelength grows in proportion to the scale factor between emission and observation. This growth is what allows redshifts to vastly exceed what any ordinary motion could provide while still maintaining consistency with relativity. Thought experiments make these points concrete. Consider two small test craft placed far apart in intergalactic space, each at rest, with respect to co-moving coordinates and with no engines firing. Their co-moving labels remain fixed. The proper distance between them increases because the scale factor grows. If the craft exchange radar pulses, each pulse moves at the speed of light locally, yet the round-trip time increases over what it would be in a static geometry, and the received frequency is shifted to longer wavelengths. If small thrusters are used to keep the proper distance fixed, each craft acquires a tiny peculiar velocity inward relative to co-moving coordinates. Relativity is never violated because the peculiar speeds required are small compared with the speed of light, and the adjustment merely cancels the gentle widening caused by the metric. In a second thought experiment, release a photon inward from a source that is currently beyond the Hubble sphere. At the instant of emission, the proper distance to the observer increases because the recession speed there exceeds the speed of light. As the photon moves inward, it can cross the evolving Hubble sphere into a region where the recession speed is lower than the speed of light, and from that point onward the proper distance to the observer shrinks until the photon arrives. The chain of local rules is respected at each step, and the result depends on the time dependence of the Hubble parameter rather than on a single number fixed in time. Observations reinforce the practical meaning of these ideas. Many galaxies show redshifts so large that when interpreted through the standard model, their present recession speeds are faster than light. The light we see from them was emitted when the scale factor was much smaller, and when their proper distances were within a range from which photons could begin a journey that after crossing changing conditions ends at our instruments. Maps of the ancient glow come from a surface that today lies at a proper distance receding faster than light, yet the photons left when the Hubble parameter and the scale factor made the path navigable. The same logic applies to the slight lensing deflections and to the correlation between late-time structure and small changes in the temperature of the glow. All are read along light paths that experience both the stretching of space and the local rule that light is the fastest possible signal. Superluminal recession therefore has no power to send a message faster than light, and no power to create paradoxes. It is a statement about how the internal geometry assigns distances between comoving points. It also clarifies why the universe does not need an exterior medium to expand into. If one imagines a boundary that moves outward faster than light through a surrounding void, then one has imported a picture from ordinary motion that the sky does not require. Distances, redshifts, and horizons are computed from the metric that belongs to the universe itself. The growth of separation at rates greater than the speed of light at very large scales is permitted because the rule for distance changes, not because anything crosses a local light beam in defiance of relativity. A final subtlety concerns energy and momentum in this setting. Photons lose energy as their wavelengths grow, a process sometimes called redshift cooling. The lost energy does not move into a reservoir outside the universe. It reflects the fact that global energy conservation is not defined in the same way in a space-time that expands and that lacks a single time translation symmetry over the whole manifold. Locally in laboratories and within bound systems, energy is conserved in the usual sense. Globally, the quantity that remains well defined is the stress energy tensor that sources gravity in general relativity, and it enters the equations that determine how the scale factor changes. This is another reminder that the expansion is an internal change in geometry rather than an exchange with anything outside. Bringing the pieces together, superluminal recession is natural, expected, and measured in its effects, without any conflict with the speed limit of light. It arises when one treats distance as a relation defined by the metric and speed as the rate of change of that relation for widely separated co-moving markers. Photons still trace the fastest possible paths. Horizons still mark the limits set by the integrated growth of the scale factor, and all of these features live within the same self-contained space-time. The calm conclusion for the central question is that what appears to move faster than light is the changing measure of separation itself, not any object racing across a fixed stage into an exterior room, and the sky's record supports that conclusion from the oldest afterglow to the farthest galaxies now mapped. Late-time acceleration enters the story when distances between far-separated co-moving points begin to grow faster than they would under the pull of matter and radiation alone. The first clear sign appears in the study of a special class of stellar explosions whose light curves follow a pattern that lets their true power be standardized. When these events are observed in galaxies at many redshifts, and their apparent brightnesses are compared with the distances predicted by a steadily slowing expansion, the explosions appear dimmer than expected. Dimmer means farther and farther at a given redshift means that the scale factor has grown more rapidly in the recent past. This quiet mismatch seen by independent teams and then confirmed with larger samples and improved calibrations points to an expansion that accelerates. The inference can be made without adopting any particular name for the cause. It follows from a simple comparison between measured brightness and redshift across a wide range. To explain the acceleration within general relativity, the contents of the universe must include a component whose effective pressure is negative enough to push rather than pull on the large-scale geometry. In the mathematical language of the theory, the acceleration depends on the sum of the energy density and 3 times the pressure. When that sum becomes negative, the scale factor speeds up. A nearly constant energy density that fills space with pressure, equal to minus its energy density, provides a clean example. More general possibilities allow the ratio of pressure to energy density to differ slightly from -1, or to vary gently with time, but the data so far favour a value near -1 without strong evidence for change. This accelerating component does not act like ordinary matter, which clumps, nor like radiation, which thins faster as the universe expands. It remains nearly uniform and persists as space grows so that its influence grows in relative importance as matter thins. The picture does not stand on supernovae alone. The angular pattern of the ancient microwave glow fixes the scale of a standard ruler at the time when the hot plasma becomes transparent. The same ruler reappears in the gentle preference for galaxy pairs separated by a certain commoving distance at later times. When the angular size and the redshift thickness of that ruler are measured across a spread of redshifts, the resulting distances and expansion rates trace the same accelerated history implied by the supernovae. Gravitational lensing adds another line of evidence. As light from distant galaxies passes through the web of matter, its path is deflected by small angles. The pattern of these deflections depends on the integrated mass distribution and on the distances that light travels at each step. When the deflections are measured statistically across large areas of sky and at several redshifts, the inferred geometry and the rate at which structures grow align with the accelerated expansion picture. Counts of massive clusters of galaxies and measurements of how quickly peculiar velocities and shapes respond to gravity provide further checks, since an accelerated background slows the growth of structure relative to a universe without such a component. Together, these observations compose a single story near flat geometry, a mix of ordinary matter and dark matter that clumps and a smooth component with negative effective pressure that drives present acceleration. The practical consequences of this component are broad. Distances at a given redshift are larger than they would be if only matter and radiation were present. The co-moving Hubble radius evolves differently, altering when light from far regions can begin a successful journey and encouraging the appearance of an event horizon that bounds what signals sent now can ever reach. The growth of density ripples into galaxies and clusters is slowed, so that surveys must see a web whose amplitude at late times reflects both the early seeds and the speed of recent expansion. All of these consequences are internal to the metric of space-time. No external room is required. The acceleration is not the outward push of a boundary into a surrounding emptiness. It is a change in the rule that assigns distances and in the way gravity responds to a component with negative effective pressure. The details of this component remain open. A perfectly constant energy density of space provides an economical fit. A slowly changing field that fills space can mimic this behavior, and could in principle vary slightly with time leaving faint signatures in precision, distance measurements in the growth rate of structure, or in the pattern of gravitational lensing. Some theories attempt to modify gravity itself on the larger scales rather than add a new component, but such models must reproduce the success of general relativity in laboratories in the solar system and in the dynamics of galaxies and clusters, while also matching the full web of cosmological observations. At present, a simple model with ordinary matter, dark matter, that clumps in a nearly constant energy density of space remains a good summary of many datasets. The proportions, when expressed as fractions of the total energy budget, indicate that the smooth accelerating component dominates today, with matter composing a smaller share and radiation an even smaller share. These statements depend on the full suite of observations and on their internal consistency rather than on any single measurement. There are, however, ongoing puzzles that motivate careful work. Distances inferred from the nearby distance ladder lead to a present rate of expansion that is somewhat higher than the rate inferred by projecting early universe measurements through the favoured model. The growth of structure measured by some weak lensing surveys appears slightly lower than the growth inferred from the same early conditions. Each discrepancy could signal new physics, hidden systematic errors, or simple statistical fluctuations. Ongoing surveys and improved calibrations are designed to test these possibilities by expanding samples, tightening control of selection and measurement biases, and adding new kinds of cross-checks such as joint analyses of lensing, clustering and galaxy motions. Whatever the detailed resolution, the existence of late-time acceleration is robust, because it rests on the overall shape of the distance-redshift relation, and on rulers and lenses that speak the same geometric language. The accelerating component also clarifies the central question of this script. One might imagine that a push must come from outside, as if space were a substance being driven outward. The observations and the theory do not require such a picture. The push is a property of the stress and energy within spacetime itself. It alters the evolution of the scale factor directly. The distances we compute are derived from the internal metric. The redshifts we measure are the integrated stretching of wavelength along that metric. The deflections we map are set by the curvature created by matter and by the smooth accelerating component within the same internal rulebook. When the rate of expansion changes from decelerating to accelerating, nothing moves into an exterior space. The relations that define distance and time evolve, and light and matter respond according to general relativity. The theme of acceleration is therefore not an exception to the earlier view, but a reinforcement of it. A final practical insight comes from imagining the future under a nearly constant energy density of space. If the component remains close to constant, then the acceleration continues, the event horizon becomes a permanent feature. Very distant galaxies fade from view as their light shifts to longer wavelengths, and their signals fall below any practical detection, and the web of structure within bound regions remains while unbound separations grow ever faster. These statements are not predictions of sudden change, but descriptions of gentle trends written by the same equation that fits present distances and by the same lensing patterns and standard rulers that trace geometry and growth. They are a direct consequence of an internal cause that acts through negative effective pressure again with no need for an exterior medium. In this way, late-time acceleration completes a consistent picture. The expansion is measured by candles, by rulers, and by lenses. Its history is read in the ancient glow and in the present web of galaxies. Its present speeding up is explained by a smooth component with negative effective pressure, whose gravitational effect is to drive the scale factor to grow more quickly. Every step in the chain is defined and tested within the universe itself. There is no boundary pushing outward into a larger space. There is only a self-contained geometry whose rate of change is measured with care, and whose gentle acceleration is one more internal fact of the cosmos revealed by light. Testing the models means asking whether many independent observations, each with its own instruments and uncertainties, converge on the same quiet description of a nearly flat, homogeneous and isotropic universe whose expansion history is governed by ordinary matter, dark matter that clumps radiation, that thins quickly, and a smooth component with negative effective pressure that drives late-time acceleration. The method is to measure distances, times angles and growth in many ways, to translate those measurements into the language of the scale factor and geometry, and to see whether a single set of parameters describes them all within their uncertainties. The ancient cosmic microwave background sets the stage by fixing the contents and geometry at the time when the hot plasma becomes transparent. Its pattern of temperature and polarization ripples encodes the densities of ordinary matter and dark matter, the amplitude and tilt of the initial fluctuations, and the near flatness of spatial geometry. These values predict the sound horizon scale, which later reappears as a standard ruler in the gentle preference for galaxy pairs, separated by a fixed comoving distance. Galaxy redshift surveys at multiple eras measure that ruler across the sky and along the line of sight, yielding angular diameter distances and expansion rates that can be compared directly to the predictions from the early sky. When they agree, the link from the hot early phase to the later web of galaxies becomes a measured bridge rather than an assumed story. Type 1, a supernovae, trace the same bridge from a different direction by using calibrated light curves to infer distances as a function of redshift. Their dimness at a given redshift compared with a steadily slowing expansion reveals late-time acceleration, and the amplitude and redshift dependence of that dimness align with the distances that the standard ruler implies when the same early conditions are projected forward. Weak gravitational lensing adds a complementary test by measuring how the shapes of many background galaxies are coherently sheared by the gravitational potentials of the intervening large-scale structure. The pattern of that shear depends on both the geometry that sets the distances along each line of sight and the growth rate of density ripples that become clusters and filaments. Redshift space distortions add another growth probe by reading how peculiar velocities squish or stretch, the clustering pattern along the line of sight. Together, lensing and distortions compare the observed growth with the growth predicted from the initial seeds seen in the ancient glow under the same expansion history that rulers and candles prefer. Cluster abundance as a function of mass and redshift provides an additional check, because the number of very massive clusters is exquisitely sensitive to the amplitude of fluctuations and to how quickly the background expands. Time delay cosmography in strongly lensed quasars offers still another geometric handle. When a background quasar is multiply imaged by a foreground galaxy, changes in the quasar's brightness arrive at different times along the different paths. Those delays combined with careful modelling of the lens mass and stellar kinematics yield distances that test the same expansion history independently of supernovae and rulers. Direct geometric distances from water mazes in circumnuclear disks tie the ladder outward without relying on brightness. Cosmic chronometers, which estimate differential ages of passively evolving galaxy populations, provide a local measurement of the expansion rate as a function of redshift. Even the lingering relics of the first few minutes when the lightest nuclei formed enter the web of tests. The measured abundances of deuterium in very metal-poor gas clouds, and the primordial helium fraction inferred from ionized nebulae, match the predictions of a hot early phase with the specific baryon density, and that baryon density agrees with the value inferred from the ancient glow, and from late-time rulers and alignment that spans more than 10 orders of magnitude in cosmic time. Each of these probes carries its own systematic vulnerabilities. Supernova distances demand stable photometric calibration across instruments, and surveys careful control of how dust alters colours and attention to how the mix of host galaxies evolves with redshift. Standard rulers require uniform selection and accurate redshifts across huge volumes, reconstruction of bulk flows to sharpen the signal, and models that account for bias between galaxies and the underlying mass. Weak lensing depends on precise shape measurement control of the point spread function and knowledge of source redshift distributions. Cluster counts require accurate mass calibration often through gravitational lensing or through the relation between hot gas properties and total mass, and they require survey selection functions that are well understood. Time delay distances need robust lens mass models, stellar velocity measurements, and accounting for line-of-sight structures. Mazers demand exquisite angular resolution and dynamical modelling. Cosmic chronometers must disentangle age and metallicity in stellar populations. The ancient glow itself demands careful removal of galactic and extragalactic foregrounds, and delicate control of instrument gain and noise. The reason to list these challenges is not to cast doubt, but to emphasize that testing the models rests on redundancy. Wherever two methods overlap, comparisons are made. Photometric systems are cross-calibrated and tied to standards. Simulations create mock skies to test analysis pipelines. Independent teams repeat measurements. Disagreements are not buried. They are highlighted as targets for further observation and improved modeling. Two such tensions illustrate the ongoing work. Distances calibrated with nearby geometric anchors and standard candles yield a present expansion rate that is somewhat higher than the rate inferred by projecting the early sky through the favoured model. Meanwhile, some weak lensing surveys report a slightly lower amplitude of present-day matter, clustering than the level implied by that same projection. Either or both tensions could relax with improved data and calibration, or they could point to subtle extensions of the model, such as small changes in the late-time equation of state of the accelerating component, a modest additional degree of freedom in the radiation background in the early era, or features in the primordial power spectrum. What matters for this script is that the framework provides a clear way to pose such questions, and a clear set of measurements that can answer them. The tests are not philosophical, they are concrete and cumulative, as surveys grow in depth and area as radio intensity mapping opens new windows on the ruler at high redshift, as deeper maps of the weak lensing shear field improve growth measurements as time delay lenses and Meases add geometric anchors, and as the ancient glow is reanalyzed with better control of systematics, the allowed space of models tightens. Through this process, the standard picture is not a guess that happens to fit one dataset. It is a measured compromise among many datasets that share a single internal geometry and a single history of the scale factor. This logic also answers the central question about expansion into an outside space. Every probe just described lives and acts within the internal metric. Rulers, candles, lenses, and time delays read angles, fluxes, and shapes along light paths that curve within the space-time of the universe. The ancient glow is a shell in time within that same space-time. The growth of structure follows the same gravitational law that the metric encodes. Nowhere in these tests does a calculation appeal to an exterior room that receives expansion. The success or failure of a model depends only on how well it predicts internal relationships between distances, times, and angles as the scale factor evolves. The intertwined success of the cosmic microwave background baryon acoustic oscillations type 1, a supernovae weak lensing redshift space, distortions, cluster counts, nucleosynthesis, time delay, cosmography, Massa distances and cosmic chronometers is therefore not a chorus singing about a boundary that moves outward. It is a set of internal measurements that, when fitted together, point to a calm description in which the universe expands because the metric that defines distance changes with time in response to its contents. That is the sense in which the model is tested and confirmed section by section, with patient attention to detail and with redundancy that guards against error. Edges that do not exist become clear when all the earlier pieces are placed together and the words are chosen with care. Expansion means that the metric, the rule that assigns distance between co-moving points at one shared cosmic time, changes smoothly with time. Curvature means that the relation between angles and distances across space follows one of a few broad forms, with observations indicating a geometry that is very close to flat within the observable region. Topology means that space can be simply connected and extend without limit, or can be finite without boundary, through identifications that cause paths to wrap and rejoin. Horizons mean that light has had only a finite time to cross the geometry, and that there are therefore limits to what can be seen today and to what can ever be seen even in the far future, with those limits defined by the internal evolution of the scale factor and not by any wall. Standard candles, standard rulers, weak lensing, redshift space, distortions, cluster counts, time delay, cosmography, geometric Messa distances and cosmic chronometers, all read geometry and growth along paths that are traced wholly within the same space-time. The ancient cosmic microwave background is a shell in time that records the moment when light last scattered in a hot plasma and began to travel almost freely to the present, carrying a nearly perfect thermal spectrum and minute ripples that reveal the early conditions and the geometry of the path to now. Inflation explains why the observable region looks so uniform and so nearly flat, and why the seeds of later structure have the statistics that maps reveal. Superluminal recession clarifies that the rate at which proper distance grows between far comoving points can exceed the speed of light without any object outrunning light locally, because the change concerns the measuring rule itself rather than motion through a fixed room. Late-time acceleration shows that a smooth component with negative effective pressure now dominates the large-scale dynamics, making the scale factor increase more quickly today than it did when matter alone set the pace. When these elements are aligned, the common picture that suggests an edge moving into an exterior space is seen to be a misunderstanding, born of mixing the everyday notion of motion with the cosmological notion of metric change. In daily experience, growth means that a material boundary pushes into surrounding air or water. In cosmology, growth means that the functional relation that turns comoving separations into physical distances evolves everywhere at once in a way that preserves large-scale uniformity and requires no exterior volume. A region beyond the present horizon is not outside the universe. It is outside the part that can be contacted today. The horizon is not a wall that advances. It is a bookkeeping boundary drawn by light travel time through an evolving scale factor. In such a world, there can be no location that counts as the center of expansion. Each ordinary observer sits at the center of that observer's observable sphere, because that sphere is defined by what has had time to arrive at that location. A typical observer in a distant galaxy will draw the same sphere around that galaxy, and will measure the same near-linear relation between distance and redshift at modest ranges, the same nearly flat geometry within the horizon, the same acoustic ruler scale in galaxy clustering and in the ancient glow, and the same evidence for late-time acceleration when standard candles and standard rulers are compared. The idea of an edge suggests a place where the metric would fail to assign distances, yet no observation requires such a failure. The metric assigns distances between co-moving points across the domain that is meaningful to discuss, and where observations cannot reach the metric still defines what these distances would be under a continuation of the same rulebook. If space is globally finite without boundary, a traveller who could journey far enough and long enough would return to the starting point without crossing an edge. If space extends without limit, the traveller would never run out of room and would never meet a border. In neither case does a wall separate the universe from a surrounding void because the interior rule for distance is complete in itself. The same logic applies to energy and to redshift cooling. As wavelengths stretch, photon energies decline. This is not a transfer to an outside reservoir. It is the manifestation of an evolving geometry in which there is no single global time translation symmetry that would support a conserved global energy in the simplest sense. Locally in laboratories and inside bound systems, energy is conserved in the familiar way. Globally, the relevant conserved quantity is the stress energy tensor that sources curvature in general relativity, and it is this tensor and its pressure that determine how the scale factor changes. The absence of a global energy ledger that balances to a fixed number at all times is not a flaw. It is the natural outcome of an expanding space-time that is not static. Another quiet point concerns images and intuition. Analogies can be helpful if their limits are respected. The expanding balloon with dots is useful because it shows that distances between dots can grow without any dot sitting at the center and without any edge on the surface. Its limit is that the balloon surface is drawn in a higher dimensional room, which tempts a leap to the idea that our space must be embedded in a higher space. The mathematics does not require embedding. The three-dimensional metric is complete and defines all of the necessary distances and times internally. Similarly, the raisin bread picture in which raisins separate as dough rises captures the increase of separations but adds a medium that flows in a way that can mislead. There is no physical ether that blows galaxies apart. There is only the changing standard by which distance is measured. To avoid confusion, the script has used internal language throughout co-moving coordinates: scale, factor, curvature, topology, horizons, and light paths. Finally, the calm answer to the title question is plain. If the universe expands, what is it expanding into? it expands into nothing outside itself because there is no outside needed in the first place. Expansion is an internal relation between co-moving points that evolves with time under the equations of general relativity given the measured contents of matter radiation and the smooth accelerating component. Distances grow because the scale factor grows. Light stretches because the scale factor grows along its path. Horizons arise because light takes time to cross the evolving geometry. The geometry is very nearly flat within the observable region, and the global topology may be finite without boundary, or may be effectively infinite, both possibilities consistent with the absence of edges. Every observational pillar that supports this picture is built from measurements of flux angle, time delay shape and redshift along paths that curve inside the same space-time. None of those pillars require or even reference an exterior room. They fit together because a single internal metric explains them. When errors and tensions appear within the data, new surveys and cross-checks refine the parameters and test for subtle extensions. The work is cumulative, the tone is measured, and the conclusion remains the same. The universe is not a fireball rushing into emptiness. It is a self-contained space-time whose rule for measuring distance evolves with time, and the entire record of that evolution is written in internal relationships that the sky supplies and that instruments read with patience and care.